All right, when we are back and we're going to do our lecture 13 frequency. Trying to make updates in my system. We're going to do our frequency response, Nyquist stability criteria, and Bode plots. So we've kind of touched on this a little bit. We did it last. We kind of introduced it a little bit abruptly to look at using essentially a frequency response and looking at Bode plots to calculate the critical gain for stability. But we're going to look at now the frequency response of our systems, and then we're going to develop essentially a way to do another stability analysis based on frequency and based on essentially what's called the Nyquist stability criteria. So we're going to use frequency domain analysis, and we're going to characterize, again, the key idea is magnitude and phase lag across different frequencies. It really is very robust, and it's really scalable. Sometimes it's often better to work in that frequency space, especially in terms of like measurements, and it's a really, really robust type of analysis. So let's say we have a sinusoidally varying input, which can be and may often be the case. And there's it will produce an output, basically same frequency, but scaled and with the phase shift. So this is going to be the new magnitude. This is going to be the new phase lag here. So this is essentially going to describe the frequency response of our system with the given sinusoidal input or command controller. So that's going to be our gain. This is going to be our phase response. And then we're going to just basically substitute from the Laplace domain S to j omega, which is just, again, the frequency domain. And j is basically going to be like our imaginary number as well. It's the placeholder. One of the cool ways, I think, to kind of think about frequency and magnitude response and phase lag is with a kind of a very simple experiment, which is you have a small coin, a penny, on a piece of paper. And you move that coin, you shake it kind of sinusoidally side to side. So you shake the paper. So you pull here, and you pull that piece of paper, and you slide essentially, and you look at how that coin, and look at basically the dynamics essentially of the coin. If you pull and slide that paper very, very, very slowly, like the actual position of this, penny or a coin, it's going to track really well with the paper. So our magnitude is going to be quite large, and like if we look at like actual position, so like again the change of that, if we were to kind of track our position here of the coin, it would move, in time. It would look like, kind of like this, going up and down, left and right, positive, negative, et cetera, et cetera. And there wouldn't be any phase lag essentially with the paper. But at higher frequencies, what you're going to see is the penny or the coin is going to slide, right? It's going to slide. There's, the friction can't maintain it. And what you're going to see is that the actual like position of that coin may get very close to zero. And basically your phase lag, like, again, the coin is going to move opposite, there's basically a 90-degree, phase lag with the paper and essentially the coin. So that's kind of an idea. I think it's a really kind of good physical one that you can kind of see what the frequency response is going to be. So let's say we're given this transfer function. Again, what we're going to do is just plug in and replace S with our frequency space. And what we then can do, and this is the basis for producing essentially our Bode and our Nyquist plots. Remember Bode plots? We actually introduced this last time. Our Bode plot gives us in decibels, and we have to convert. So to get the actual magnitude, you'll read it off the graph and then solve for this value here. Phase plot, that's just a read off. So it's really, really nice, and we can kind of look at those values there. So it's pretty good. There are some critical transfer functions where it's good to kind of know and like see how the Bode plot responds, but again, we'll take it piece by piece. Now, this is really kind of important. Nyquist plots. We haven't introduced that yet. So let's say I have this transfer function. I could replace basically the transfer function, and I can look at my Bode plot for that transfer function. Now, the Nyquist plot looks like this. Now, how do we interpret this Nyquist plot for that transfer function GS1? Well, let's kind of take it step by step, and we can look at the GS1 right there. how can we construct that Nyquist plot from essentially the Bode information? So what we're going to do, it's a parametric plot. So again, it's real, and then it's essentially just our imaginary component. And that's our frequency response. So the way that we can construct it, there's one method is that you increase frequency from +0 to infinity. And essentially you can look at the gain and phase and so basically you can go and look at and say, okay, well, here's a positive frequency, and we can kind of look at the magnitude and coordinates effectively. So you're drawing a vertical line here. Actually, I'm going to do something pretty cool. Let's go here. So one idea or one method, and it's kind of laborious. I'm taking a screenshot right now, so sorry. Oh, perfect. I almost messed it up. So one method is, can I move this? Exactly. Here we go. So you can draw basically vertical lines here. It's okay, at this frequency, and as you you go across, and then you map out essentially on the real and on the imaginary side, you basically sketch out the gain and the phase at those sample points, right? So the gain, you're basically recording those values. And essentially you can map out and mirror essentially across the real axis for negative frequencies, right? So the real axis is here. So these are for positive value or positive, and you can mirror essentially on the other side. And then you basically indicate with arrows the direction of increasing frequency. So if we were to kind of say, let's look at here. So if I look at basically here, and we can kind of see where essentially it's going to move, and the arrows essentially indicate that value. So that's one method, is essentially sketching it out here, correlating it, and see where essentially the angle is going as you increase essentially frequency. And remember, you're going to look at that real and imaginary response, and we can actually essentially see it through here. Now, the second method, you can just use this in Mathematica, is just by plotting it here. So let's look at this transfer function, and let's kind of start to break this down. So if I look at here, if I look at 0 frequency, our value of our function is basically equal to 1. So we're going to basically look at 0 frequency, my value on that x-axis is going to be equal to 1. As we start to, and it arcs towards the origin in that 4th quadrant, right? And it's never going to essentially encircle here. And we can kind of see at omega equals 1, we get essentially this phase lag at 45 as well. So we can essentially see these, they're doing construction here. You can see at an omega of 1, you get a phase lag of minus 45. So you can kind of start and you can essentially sketch those out. But again, we have those and we're going to analyze that a little bit more importantly. We could look at different systems here, and essentially you can see resonant frequency, and you'll see these are Bode plots, and then you'll see actually this kind of very different behavior here. But actually we can look at it, because if we look at omega, excuse me, it's very annoying. But you can kind of see essentially these different Nyquist plots here. Now, and you can do the same thing for another system, for this system here, and you see this peak, and then our plot. So, fairly straightforward on how we can, and honestly, it's not really the sketching out method is really not one that's going to give you a tremendous amount of insight. And there's tools now that essentially are going to create your Nyquist plot immediately, and you can see some of that behavior. Now, the key aspect that we're going to go through now is looking at stability by developing essentially our Nyquist criteria and our Nyquist stability criteria here. And we're going to define that next time. So, see you next video. Thanks. Bye.